Ohm's law is the relationship between voltage, current, and resistance. It is expressed mathematically as I equals V over R, where I is equals to current, V is voltage, and R is resistance. The unit for current is A, voltage is V, and R is omega. Ohm's law. The amount of current is proportional to the voltage or potential difference applied to the circuit and inversely proportional to the resistance of the circuit. This is a simulation app regarding Ohm's law. We can observe the higher the current and voltage, the lower the resistance. And the lower the current and voltage, the higher the resistance. It also shows the resistance opposes the current flow. Let us know what is resistance, current, and voltage. Resistance is the measure of the opposition to current flow in electrical circuit. It is measured in ohms, symbolized by Greek letter omega, established 1827. It is named after German physicist Georg Simon Ohm. Current, rate of flow of electric charge. Voltage, pressure from an electrical circuit's power source that pushes charged electrons, current, through a conducting loop, enabling them to do work, such as illuminating a light. This is a simulation on resistance in a wire. We can observe the resistance of a wire is directly proportional to its length and inversely proportional to its cross-sectional area. Resistivity is the physical property of a particular substance which is having particular dimensions. How can I apply Ohm's law in actual installation? Example is, I have an electric stove in my kitchen. Heating element stopped working. I decided to check if it is burned. I measured the resistance, which was R equals 40 ohm. Therefore, from Ohm's law, I calculated current IV over R equals 220 volts over 40 ohm equals 5.5 ampere. It means that my heating element is fine. Now let us know the examples of loads, conductors, and power sources. Loads. There are three types of loads: resistive electrical loads, capacitive, and inductive electrical load. In electrical load, it includes a light bulb, a resistor, and a motor. Load is any device in the circuit that produces light, heat, sound, or electrical movement when current is flowing. Resistive load consume electrical power. Examples are incandescent lamps and electric heater. For capacitive, the system will only have real power if there are equal amount of both loads. Examples are capacitors, variable or fixed capacitor banks, motor starting capacitors, generators, and synchronous motors. For inductive, it is any devices that have coils in them. Examples are motors, solenoids, contactor coils, compressors, speakers, relay, transformers, inductors, and power generator. Now with conductors, it is a substance in which the electrons can flow into its body. Examples: copper, aluminum, gold, silver, seawater, concrete steel, and iron. With semiconductors, it is a substance, usually a solid chemical compound, which can conduct electrical under certain circumstances. Examples are germanium, that are used in electronics, silicon, antimony, arsenic, boron, carbon, selenium, sulfur, and tellurium. Now with power sources or electric power supply, it is a source of electrical charge, such as battery or power line, employed to furnish the tubes and semiconductor of an electric circuit with proper electric voltages and currents for their operation. Examples are electricity is generated with steam turbines using fossil fuels, nuclear biomass, geothermal, and solar thermal energy. Now let's have a sample problems on Ohm's law. Sample 1. An electric device has a resistance of 18 ohms and a current of 15 ampere. What is the voltage across the device? Solution. Resistance, current, and voltage are related by Ohm's law as V equals IR. Thus, the voltage of the device is obtained as V equals IR. The value of I is 15 amperes multiplied by 18 ohms is equals to 270 volts. For the formulas, to easily understand the three formulas of Ohm's law, we can draw the Ohm's law triangle V over I times R, where we can cover the letter on what we are looking to obtain the formula. Example, we are looking for V, voltage, then we will cover the V. It is V equals I times R. For current, we will cover the I, then V over R. While resistance, we will cover the R, it will be V over the current. Let's go ahead with sample 2. A 3 voltage potential difference is applied across a 6 ohm resistor. What is the current that flows into the resistor? Solution. Ohm's law states that the potential difference across a resistor is resistance times current, so we get I is equals V over R is equals to 3 over 6. The answer is 0.5 amperes. Last sample. In the following circuits, find the unknowns. Solution. In the left circuit, the current through the resistor is as in milliamps. Thus, I is equals V over R is equals to 120 over 100 is equals to 1.2 amperes. To convert it to milliamperes, multiply by 1000, so we get I is equals to 1200 milliamperes. In the right circuit, the resistance of the light bulb is known. Thus, resistance equals voltage over current is equals to 24 over 600 times 10 to the power of negative 3. It will be resistance equals 40 ohms. Now let's go ahead with magnetism and magnetic circuits. Magnetism is a force that attracts. It pulls closer, or repel, pushes away. Objects that have a magnetic material, like iron, inside them. Magnetic objects. Magnetism is caused by the motion of electric charges. Every substance is made up of tiny units called atoms. Each atom has electrons, particles that carry charges. There are theories related to magnetism and electricity.
Faraday took a simple ring of iron and wound two pieces of copper wire around it. Nothing so extraordinary about that, thought the gathered audience. But then he added the key ingredient, electricity. When one of the wire coils was connected to a battery, or a voltaic pile as they called it back then, an electric current flowed through it. But here's the funky part. There was also a current in the second coil. Suppose the second coil was connected to a light bulb. For a second, the audience would have seen the bulb flash. The two coils were not connected to each other in any way. They were insulated so no current flowed in the iron ring. So, how on earth did electricity jump from the first coil to the second one? It did not jump, it was induced. This was the great revelation of Faraday, that an electric current in one piece of wire could induce another current in another wire. But what exactly is induction? Let's go back to the modern age and look closer. It turns out that when electricity flows along a wire, it creates a magnetic field. The lines of this magnetic field curve around the wire in circles like rings around a finger. I'm going to take this loop of wire and stick it inside the magnetic field. The loop contains something called a galvanometer, which is a very sensitive ammeter for measuring tiny currents. Watch what happens. When I insert the loop into this magnetic field, the galvanometer moves. It is detecting a small current. I take the loop out again, and the galvanometer moves again. But if I just hold the loop still like this, there is no current detected at all. My instrument doesn't move. It's only when I move the wire into or out of the field that I get a response. Faraday saw this too, and he realized that an electric current was induced by a changing magnetic flux. Flux is given by the strength of the magnetic field multiplied by the area of the loop moving through it. In order to get a current inside the loop, the magnetic flux must change. This only happens when I stick the loop into the field or take it out. When it's completely inside the magnetic field or completely outside it, the flux does not change. This is induction, ladies and gentlemen, the manipulation of electricity through a changing magnetic flux. Today we call it Faraday's law.
This coil here, there is a current going through this coil. It creates a magnetic field, but because the permeability here is very high than the permeability of air, all the flux would be going through this core. So the magnetic flux or the magnetic field lines are localized, breaking much inside this core. Sample problem in magnetic circuits. Sample 1 is a magnetic circuit where a single air gap is shown. The core dimensions are cross-sectional area having 1.8 times 10 to the power of negative 3 m squared. Mean core length LC is equals to 0.6 m. Gap length is 2.3 times 10 to the power of negative 3 m. And N is 83 turns. Calculating the core RE and the gap RG for current of 1.5 A and calculating the total flux, the flux linkages of the coil and the coil inductance are shown in the solution. Sample 2 is considered the magnetic circuit with the dimension of problem 1, assuming infinite core permeability. Calculate the number of turns required to achieve an inductance 13 mH, the inductor current, which will result in a core density of 1.0 T. It is shown in a solution for the inductance and the flux density.